Good morning. In today's lecture we will see some new ways to prepare alcohols, and many of these new ways rely on use of organometallic reagents. Now, organometallic reagents are a class of organic or organometallic compounds that we haven't seen so far, and these compounds are characterized by a direct bond between carbon and a metal. Now, note that this is a bond between carbon and a metal, which means that alkoxides, for example, the compounds that can be derived from alcohol by reaction with sodium or potassium, are not organometallic compounds because they don't have carbon-metal bond, they instead have oxygen-metal bond. Now, the interesting thing about organometallic compounds is that, and these are the two most common types, the organomagnesium and organolithium compounds, is that most metals have electronegativities in the range between 0.7 and 1.7. In other words, significantly lower than electronegative elements we've been used to talking about in the first half of this course, and also significantly lower than carbon. So both of these bonds are polarized, with the negative ends being at the carbon, which means that these carbon atoms in these organometallic compounds are nucleophilic. This is something that we don't see too often. Carbon atoms are typically electrophilic because they're bound to electronegative elements such as oxygen, nitrogen, chlorine, and so forth. But we have seen an example of this in acetylides, which we can deprotonate through the use of sodium amide to give us an acetylide, an acetylene salt. And this acetylene salt can now engage into SN2 reactions or into addition of the carbonyl compounds, which then ultimately gives rise to alcohols. But acetylides are a little bit of a special case because acetylenes and other alkynes can be easily deprotonated because of their acidity. However, we cannot apply the same method to alkyl or alkenyl-based reagents since alkanes and alkenes are not nearly as acidic as alkynes are. And so how do we make these organometallic compounds for alkyl and alkenyl? Let's see. The organomagnesium compounds, which are the most common ones, are also known as Grignard reagents, after French chemist Victor Grignard, who developed them in 1905 and shortly afterwards got a Nobel Prize in 1912 for the development. And these reagents are made through the reaction between alkyl halide and magnesium. This is elemental magnesium. This is typically performed in ether solvent, which has the dual role of first solubilizing everything and then also coordinating to the metal in the organomagnesium compound. And then we get our MgX. And this is a Grignard reagent, which for many purposes is equivalent in its behavior to R minus MgX plus. Now, although we will use this formula RMGX a lot, one needs to say that this is really a very inaccurate representation of what is actually going on in solution, because in solution it is probably likely that this magnesium species is extensively coordinated and possibly dimerized or tetramerized with molecules of ether. So the ether is really a necessary solvent, and we're going to simplify its role just as a solvent, but certainly helps the coordination of magnesium species. Now this X can be chloride, bromide, or iodide. Rarely are fluorides used. And the reason for that is that the reactivity of fluorides is not sufficient. So iodides are mostly reactive, followed by bromides, then chlorides, and then much lower are fluorides in the rate of formation. And an example of this, we take phenyl bromide and treat it with magnesium in ether. We will get magnesium bromide. Alternatively, if we can use this on cyclohexyl systems. So if you have this chloride, and again treat it with magnesium in ether, we'll get cyclohexyl magnesium chloride. We can do this on these alkenyl-based iodides. Again, magnesium in ether gives us this iodide. Another class of organometallic compounds are alkyl-lithium compounds. And they are similarly easily made. So again, we start with Rx and 2 molecules of lithium, 2 atoms of lithium, and this gives us our lithium plus LiX. And this can be done in either ether or alkane solvents. For the reason that we'll see in the next subsection, we'll see why this cannot be done in alcohols or in acetone or similar solvent. To just exemplify this reaction, if you take vinyl chloride and expose it to 2 equivalents of lithium, we'll get vinyl lithium and lithium chloride. If you take this butyl iodide or many others, we'll get butyl lithium, which is a very common organometallic compound, and it has huge use in pharmaceutical industry. Even though it's an organometallic compound, it's still reasonably affordable to produce because it's produced from simple butyl halide and lithium, which is again a relatively cheap metal. And alkyl lithium bond is more polarized than alkyl magnesium. Which means that there is more of a ionic character to alkyl lithium compounds, which in other terms means that our group in alkyl lithium compounds is more nucleophilic than organomagnesium compounds, and it's thus more reactive. Now, in the next subtopic, we'll see how these actually react with alcohols, with carbonyl compounds as well as alcohols.